There is such a mysterious and uncatchable quantity in physics which is not directly measurable, and it doesn't even have a single definition because it changes depending on the framework in which it appears. We're talking about entropy, from ancient Greek inner transformation. Although entropy is an elusive concept, it's curiously ubiquitous, such as an invisible dark halo that surrounds and cloaks our universe, so that it takes different appearances and facets from time to time. If it didn't exist, physics in our universe would be very different. Entropy has appeared during the history of science in different areas and moments independently. It was first defined by thermodynamics during the Industrial Revolution. Then it was described by theoretical physics until the 19th century, when it was introduced in the information theory and then extended almost to any other area of science. Entropy, the game you're not allowed to play. In thermodynamics, as we're about to see, entropy measures the tendency of the energy in the universe to degrade and to spontaneously evolve towards messier and unstable energy forms for human activities. As a matter of fact, energy sources are not all the same. There are different types, as well as food. There are better sources of energy than others. In nature, the more energy is concentrated and stored in ordered structures, the more is exploitable. Kinetic energy potential, chemical, nuclear, wind are all usable energy sources. These are suitable to produce forces for generating movements and doing work. Thermal energy, by contrast, is related to heat production and is considered unusable energy because it cannot be converted in exploitable energy. We'll clear up why later. During the first Industrial Revolution, the invention of the steam machine had generated great enthusiasm, and scientists and engineers of that time had been working hard, attempting to improve efficiency of thermal machines in order to produce energy for industrial purposes. All the efforts were aimed at realizing a dream, to build the perfect thermal machine, a device capable to convert the whole absorbed heat in usable energy, in a perpetual motion with no loss. A possibility was very suggestive and debated, building a boat capable to absorb the heat in the sea and completely convert it in continuous propulsive energy. Physicists and engineers soon clashed with difficulties and experimental limits, which turned out to be sides of the same coin, different aspects straight related to the concept of entropy. Hopes were nipped in the bud by British physicist William Thompson, also known as Lord Kelvin, who claimed an experimental principle based on his studies on heat. This is now called the second principle of thermodynamics. It is impossible to produce a transformation in which the only result is to absorb an amount of heat and to completely convert it in work. This statement was also experimented years ago by Sadi Carnot. The French engineer was one of the first at the beginning of the 18th century to systematically study the working cycles of thermal machines. He guessed that their efficiency should have a limit impossible to overcome because energy loss could never be eliminated. Carnot understood that heat and temperature were strictly related. He realized that it was precisely the variations in temperature that triggered the heat flows that allowed a thermal machine to do work and produce energy. He was among the first to perceive that the energy generated by a thermal machine only depended on its working temperatures, while was totally independent from its technical and design features and from the substance used in order to perform the transformations. It could be a gas or another one fit for the purpose. In 1864, the German physicist Rudolf Clausius, starting from Carnot's work, claimed an asymmetry in the flow of heat. In nature, we observe that heat always flows from a hotter body to a colder one, while the reversal process doesn't happen spontaneously. This seems obvious nowadays, but there wasn't any physical law that accounted for this. Starting from this observation, Clausius stated a principle which is today an alternative version of the second principle of thermodynamics. It's impossible to perform a transformation in which the only result is to transfer heat from a colder body to a hotter body. Clausius understood that in order to do so, energy or work from the environment was needed. Otherwise, the transformation would never occur spontaneously. Let's think about our fridge. We realize that it can reverse the spontaneous flow of heat to cool down the food we put into it. However, in order to do so, it must necessarily be connected to a power outlet and absorb energy. Otherwise, transformation would never occur spontaneously, and our fridge would not be able to perform the refrigerator cycle that lets us preserve our food. Our fridge is nothing more than an inverted thermal machine. First prototypes were designed right around this time. Carnot, then Kelvin and Clausius, but also Joule, Clapeyron, and other great minds independently realized that whereas heat and work are energy forms strictly related, they are not symmetrically replaceable with each other. In attempting to assess the energy loss within thermal machines, Clausius wanted to define a quantity to measure how much energy degrades in heat during a transition. Thus, he defined the variation of entropy of a system during a reversible process as the ratio between the heat exchanged by the system and its temperature held constant. All experimental observations and statements related to the second principle can be therefore summarized by introducing entropy. In every real thermodynamic process, the entropy of an isolated system can only increase. By measuring the variations of entropy, come out that every natural process evolves spontaneously by increasing its entropy. Some heat is always produced, and fatally more and more energy is unusable until it becomes totally degraded. Following the entropy principle, in a very distant future, the whole energy of the universe is going to be unusable. At that point, temperature is going to be the same everywhere, and the thermal death of the universe will occur. Heat and work are very similar sources of energy, but not interchangeable. They cannot transform symmetrically into each other. While work can always be completely converted in heat without producing any other change, the other way around is not allowed in nature. Or better to say, it could be theoretically possible, but only at one condition: at the temperature of absolute zero. In 1848, Lord Kelvin had expressed the concept of absolute zero as the temperature at which matter is perfectly still without any thermal agitation motion. Here, the third law of thermodynamics joins the game. It was formulated for the first time between 1906 and 1912 by the German chemist Walther Nernst, and for this reason it is also often called Nernst's theorem. It states that to reach absolute zero in a thermodynamic process involving a finite number of operations is not possible. Why is it impossible to convert thermal energy in usable energy? This has a precise microscopic explanation. When a body is heated, thermal energy works by speeding up the velocity of its molecules, increasing mean kinetic energy, and consequently temperature. However, every single molecule of the body has a different agitation direction. If the kinetic energy of a macroscopic body is, in a certain way, directional, because all the molecules move in the same direction, by contrast, thermal energy is a form of messy and non-directional kinetic energy. What is the deep reason why entropy spontaneously increases? Why does nature behave this way? The great theoretical physicist Ludwig Boltzmann answered the question in 1871, giving a probabilistic insight based on the microscopic behavior of the particles. Boltzmann considered macroscopic systems, like a gas, as made up by a huge number of components, each one with a position and a velocity in every moment. You realize that every system spontaneously evolves starting from less likely states towards more probable ones, and the most probable physical state is the balance. Let's consider the free expansion of a gas in a recipient separated in two parts by a partition. At first, the gas is confined in one part, but when we eliminate the partition, we observe that spontaneously it starts to expand until it occupies all the available space in the recipient. We can observe that once the expansion has started, there's no way to reverse the process. The gas will never return confined to the initial part of the recipient. There are no constraints preventing the gas to do it, but it's highly unlikely that such a huge number of molecules, billions and billions, all move in the same part. It's equal to flip the coin billions and billions of time, obtaining heads every time. Therefore, it doesn't happen spontaneously. It can be proved that the most likely configuration is that with the particles distributed across the recipient. Let's now imagine a puzzle in a box, made up of thousands of pieces. There is only one configuration in which all the pieces together compose a complete picture. By contrast, there are a huge number of different arrangements where pieces are messy and don't compose any picture, or compose only a partial picture. Let's imagine the complete puzzle in the closed box. After having shaken and reopened the box a few times, we observe that the arrangement of the pieces from time to time will be messier and messier. The system tends to evolve towards the most probable configurations, those with the most different ways to happen. The probability that after a shaking the puzzle gets back to compose a complete picture is so low that never occurs. Boltzmann identified entropy with the probability to find a system in a certain state. He realized that the most probable states are those with more different ways to occur, those who contain a higher number of allowed microstates. These are all the possible combinations in the arrangement of the system components associated with a certain macroscopic state. In other words, what can happen in many different ways has a higher probability than what can happen in only one way or in a few ones. You can lose to the lottery with all the combination, but only one wins. Mathematically, Boltzmann related entropy with the number of microstates associated to a macroscopic state. We can demonstrate that this is equal to the definition of Clausius. In this way, an increase of entropy involves an increase in the number of microstates accessible by the system, and therefore an increase in disorder. This law is carved on his tombstone in the Central Cemetery of Vienna. The new probabilistic approach adopted by Boltzmann was fundamental because it paved the way to a new physics. The founding father of quantum mechanics were afterwards strongly inspired by this new insight, from Planck to Einstein, from Schrödinger to Bohr. Starting from the 20th century, entropy was extended in different research areas. In 1948, the American computer engineer Claude Elwood Shannon introduced entropy in the framework of the information theory, describing it as a loss of information in a system. The more a system is well ordered, the more definable with as little information as possible. The more is messy and chaotic, the more information is needed to describe it. Shannon demonstrates that a closed system cannot increase its content of information. It will only decrease or at best stay constant in an ideal process. So entropy tells us that a cassette, a compact disc, a vinyl record, a book, all these mediums are going to lose their information over time and won't ever recover the original information. There's a funny way to resume the game of entropy by using the three principles of thermodynamics. The first one says that you cannot win. The second one says that you cannot even draw. The third one says that you cannot even play. We are forced to play a game we are going to lose. If you'd like to help improve the quality of our content, please check us out on Patreon. We would like to say a big thank you to all those who show their support.